Swayam Prabha. Digital India. Educated India.
Having picked a subset, they switch to some improving action in that subset. Okay. Again, that maybe is just left arbitrary right now as to which improving action you pick. I mean, if you want, you can do that also at random, right? Or maybe you have a fixed preference in the actions. But regardless, it is still random because the states that you are switching are picked randomly. Okay. So this is another example. Here's yet another example, which is called simple policy iteration. So simple policy iteration is going to assume that, let's say the states are numbered 1 to n. Okay, in fact here they are numbered 1 through 8, right? S1 through S8. So the rule is very simple. You will only switch one state at a time. That state will be the improvable state that has the largest index. Okay, if you're looking at it pictorially, then it means it will be that improvable state that is the rightmost. Okay. So in this case, you will switch S7. You will not switch any of the other states. Okay, you will only do one at a time. Again, which improving action? Let's say that's arbitrary. Okay. In fact, notice that if you have only two actions in your MDP, right? If k equal to 2, then actually you don't have a choice as to which improving action you will pick to. You will switch to, because there's only one improving action. If at all there is an improving action, right? So your sort of hand is forced if k equal to 2. Okay, but if k is more than 2, in general, you can have more than 2 improving actions. And so you have to exercise that choice one way or the other. All right, good. So you now have some flavor of different variants of doing policy iteration. The most common is Howard. In fact, when people say policy iteration, by default, a lot of people mean Howard's policy iteration. Okay, Mansoor and Singh and simple policy iteration, of course, are there in the literature. They're not very commonly studied. Okay. All right. So what is the big unfinished business that we have, which is what is coming up next, is for us to prove the policy improvement theorem. Believe it or not, you already have seen all the basic building blocks that we need to prove it, with the exception of one concept, okay, which formally we have not defined, but is very similar to something we have seen. So we will begin with a definition of what is called the Bellman operator. Okay, this is the Bellman operator, denoted B pi. Okay, so this must naturally remind you of the Bellman optimality operator B star, but B pi is different. Okay, so remember that B star was an operator that we defined for every MDP. B pi is defined for every MDP and every policy pi. Okay, so there is one B pi for every pi, even for the same MDP. And what is B pi? So like B star, B pi is also a mapping from, let's say, n-dimensional vectors or mappings from states to numbers to such mappings. Okay, and the definition for when it is applied to X, right, which is such a mapping, B pi of X of S, okay, is defined to be sum over S prime T of S pi of S prime times R of S pi of S prime plus gamma times X of S prime. Okay, so this is how it depends on X. But notice the difference with B star, right? B star would have an A, right, instead of pi of S, and a maximization outside over actions A. Okay, here pi is a part of the definition of it's B pi of X, right? So pi of S is the action that is taken to make the transition happen. Okay. All right. So again, just to reiterate, there is one such Bellman operator for every policy pi. In pi, there's no max going on like B star. All right. Now, we did all of this for B star. We can do very similar things for B pi. I'm not going to do them, but you can maybe take this up as homework. It will follow the same principles as what we did with B star. Okay, so 3 things to state. Just like B star was a contraction mapping with contraction factor gamma, so is B pi a contraction mapping with contraction factor gamma. Okay, in fact, it's easier to prove that B pi is a contraction mapping than to show that B star is a contraction mapping. All right. So you can look at Chaba Sepeshwari's book, and you'll, in the same chapter, right, the appendix, you will find this proof. B pi, if you apply it like, because it's a contraction mapping by Banach's fixed point theorem, you keep applying it, it's got to have a fixed point, right? So just by the definition, you can see that the fixed point is V pi. Okay, so because if you put V pi here instead of X, right, notice that this looks like Bellman's equations, and therefore we will get V pi. So the fixed point of B pi is V pi. Okay, that's the second thing which should ring a bell, right? So one legitimate way to compute V pi, right, is to actually start at any arbitrary X and then just keep applying the Bellman operator B pi. Okay, remember this is what we did to get V star, right? We started at some X and kept applying B star. That was the value iteration algorithm. If you just fix your policy pi and keep applying B pi, you will get to V pi. Now the reason this is not so popular is, I mean, you can anyway solve Bellman's equations, which are linear equations, right? You can solve them using a solver, and that is usually more efficient, right? It gives you an exact answer as opposed to doing it iteratively. There's really no need, okay, to be solving for V pi using this iterative approach. With Bellman optimality equations, they were non-linear, right? So we needed some way to solve, and the iterative approach was a reasonable way to solve, okay? But it remains that the fixed point, right, V pi can be reached by applying B pi over and over and over again, okay? And the third thing is that B pi also preserves greater than or equal to, okay? So if X is greater than or equal to Y, then you apply B pi to both sides. So B pi of X will be greater than or equal to B pi of Y, okay? This is again something you can prove from first principles, okay? The one not so obvious thing, but which you can verify by just writing things down and carefully looking is what I have written down here, okay? So let's take two policies, pi and pi prime, okay? Now, the claim is that B pi prime applied to V pi, okay? When you look at that, then the element S, right, that is going to be the same thing as Q pi of S pi prime of S, okay? So what is Q pi of S pi prime of S? It's the expected long-term reward you will get by taking pi prime for the very first time step, and thereafter acting according to pi, right? So notice that that's what will happen if you apply B pi prime to V pi, okay? You're going to get transition according to pi prime, okay? But then here onwards, gamma times, you're going to get V pi, okay? So it's basically going to be the same thing. This is just an observation, okay? But it's useful to know this equivalence because we're going to start our proof of the policy improvement theorem based on this observation, okay? All right, so that's what's coming up next, the proof of the policy improvement theorem, which will primarily apply B pi. Okay, so make sure you understood Bellman operator. Okay, here's the proof. Okay, there's two things that we have to prove. The first is that if pi has no improvable states, then it's an optimal policy, right? So here's a sequence of steps for doing that. So if pi has no improvable states, then what it means is if you look at the Q value of any action, right, that's going to be less than or equal to the value for every state in pi, okay? And if you just write that down in a more succinct form, what you have is that for every pi prime, okay, V pi will be greater than or equal to B pi prime of V pi. Okay, remember on the previous slide we said that this is going to look like Q values for each state, right? So basically what we're saying is every Q value is less than or equal to the corresponding state value. Okay, just convince yourself about this step. But now we do the same technique that we did with B star. Okay, you just apply B pi again to what we have. We have that V pi is greater than or equal to B pi prime. So apply B pi prime again. Okay, so then what we will get is that B pi prime of V pi is greater than or equal to B pi prime squared of V pi. Okay, and this is because of B pi prime preserving greater than or equal to. And so now you have a chain with three such elements. You can keep doing this over and over again, but we know that as we take the limit of B pi prime as to the L, right? As L goes to infinity, what we have is, by Banach's fixed point theorem, V pi prime itself. Okay, so just by applying B pi prime, right, multiple times, what we've shown is that if pi does not have any improvable states, then it is greater than or equal to every policy pi prime. Okay, so that's the definition of an optimal policy, right? This means that pi is an optimal policy. So we've done part one of our proof. The second thing you have to show is that if pi does have improvable states, right, and you're going in some way from pi to pi prime by doing policy improvement, then we have to show what? We have to show that pi prime strictly dominates pi, right? It's greater than pi. So how do we show that? Same idea. You can see that the statement that we started with implies that B pi prime of V pi is greater than V pi. So in fact, what it means is pi prime that you go to, right, will have its corresponding Q values, right, at each state be strictly greater than where you have improved, and where you have not improved is going to be the same, right? So that's the reason you get B pi prime V pi is strictly greater than. And this is also the reason our convention was to define improving actions as ones that actually have strict greater than in terms of Q value. Okay, but now that we have this, we apply B pi prime again, and we find that B pi prime squared of V pi is also greater than V pi, etc. And you take the limit, you have that B pi prime is greater than V pi. Okay, which is another way of saying that pi prime dominates pi, right, with strict domination. So there you go. All right, we have just proven the policy improvement theorem, and therefore, right, we've from the ground up, right, now proven that there is an optimal policy, right, and that optimal policy's value function is the optimal value function of the MDP. Okay, now there is one small aspect that I think bears discussion. So I'm going to do it somewhat informally as a part of the lecture. Okay, I will also follow this up with a more technical write-up. I'll tell you why. Okay, that I'm not really introducing it here. It would get a little bit notation heavy for me to do this portion in full as a part of the lecture. But what is this portion? What am I coming to here? So, in principle, okay, an agent that is living in the world, right, the policy that it follows does not have to be mapping from states to actions, right? It can actually remember what happened along states that it visited, right? And even from the current state, right, it can have an entire probability distribution over action, right? So let us say that capital lambda, okay, this kind of V, inverted V is like a capital lambda, okay? Let capital lambda be the set of policies little lambda, which comprise all policies that are written down as mappings from histories, okay, the set of histories to the set of probability distributions over actions, okay? So the first thing to note is that capital lambda is a superset of the policies that we consider, right? We only considered policies capital pi, which were Markovian, okay, which were mapping from states to actions. And not only Markovian, they were stationary in the sense that the policy did not change with time, and it was also deterministic. Okay, we didn't think of doing distributions over actions. So strictly speaking, pi is a subset of it's a proper subset of lambda, right? What we've shown, right, on the previous slide is that there exists a pi star in pi which is greater than or equal to every pi in pi. Okay, so this is what we have shown. But the question remains, right? Could it be that there is some lambda in capital lambda, right, which is not dominated by pi star, right? Could it be that there is a policy which is maybe non-Markovian, maybe non-stationary, maybe stochastic, right? One of these other things, on account of which, from some state, it's actually able to do better than pi star, right? I mean, we have not proven that such a policy cannot exist. Okay, so the question is a legitimate one. Does there exist a lambda that is in capital lambda but not in pi, such that it is not true that pi star dominates, is greater than or equal to lambda? Okay, which is another way of saying there is some state from which lambda can give you better value than pi star. Okay, so the answer to this question is no. Okay, so what I'm going to give you is some intuition as to why it is no. It gets a little bit notation heavy to write down the full derivation of this. So I'm not doing it as a part of the lecture, but I will follow up by putting up a note on the class web page that if you're interested as a reference, you can see. Okay, it's a reference. It's not like mandatory reading. You don't have to do it if you don't want. If you want, you can see it. Okay. All right. So what is the intuition I want to give you for why we don't need history, why we don't need stochasticity? It's this reason. Okay. So in an MDP, right, the consequence of an action, right, when you take an action, what happens, that depends only on your current state, right? It's T of S, A, S prime. It is R of S, A, S prime, right? T and R don't depend on where you came from. It depends on the state in which you are currently. And crucially, the agent knows at any point of time in which state it is. Okay, we have assumed, right, that the agent can take an action depending on state. Right? The assumption here, although we didn't say it explicitly, is that an agent knows in which state it is, right, and therefore it can apply its policy and take the corresponding action. So the fact that future is conditioned on state and action is one important reason. It does not help to remember where you came from. It does not also help to do multiple things stochastically. The second aspect, which is also needed, is the fact that we have defined values to be infinite discounted reward, right? Which is an infinite sum over time of expected discounted reward. Okay. By virtue of this definition, right, it happens that at any point of time, right, if you ask the question, what is the right thing for me to do here onwards? In principle, it is the same thing at every point of time. The right thing to do at every point of time is to maximize the expected long-term reward starting from where you are right now. Okay, so this is because expectation of a sum, right, is a sum of expectations. It's on account of the fact that expectation decomposes like that, that wherever you have reached, right, the right thing to do now onwards, right, is the same, right, as it would be had you started here the first time. Where you come from does not matter. The other part of this is that your horizon is infinite, right? Even if you spent 10 time steps doing something, what is left, right, is infinity minus 10, which is infinity, right? It's always infinity. It never becomes less. So sort of informally, these are reasons that it does not help to remember or to be stochastic. By contrast, let me show you a few cases where history and stochasticity actually could help. Okay, in general, they can give you better values. So one very popular class generalizing MDPs is what is called POMDPs. Okay, partially observable MDPs. So the idea in a POMDP is what the agent senses at every point of time need not be state. Okay, it is what's called an observation, and an observation can be a reasonable proxy for state, right? But there might be some loss of information. So, for example, at any point of time, I am seeing in a certain field of view, right? Maybe 120 degrees or 160 degrees or something like that. I cannot see what's behind me, right? So what I'm getting is an observation, but I make like a reasonable reconstruction of state based on my observations, right? Maybe 2 seconds back, I had looked back, right? So I remember what is going on behind me, and then I look here, right? And then I look there. In a few steps like this, right, I can more or less reconstruct what the state is around me, right? Even if I can't see the entire state at every point of time. So you already see, right? It helps in this case for you to remember what you saw 3 steps back, 4 steps back, 5 steps back, right? And history, right, is a way of disambiguating state. Okay, so in POMDPs, actually policies will be mapping from what is called belief states, right, or sometimes just histories to actions. Okay, and there too, actually, stochasticity can help. It might sometimes help you to take actions probabilistically. When we actually defined this in week 4, right? We said one way of defining long-term reward is called finite horizon. Right? You just define reward to be the aggregate reward over the next 20 time steps, let's say, right? Where 20 is a fixed constant. So if this is the case, right, in general, you can do better by having non-stationary policies, okay, policies that depend on time. So if you have 20 steps to go, the right thing to do right now, right, the 20 steps to go from a state could be different from what is the right thing to do if there's only 2 steps to go, okay. And so you will strictly be better off, right, in many cases by having a policy that depends not only on state but also on time. Another example is in a non-Markovian setting like a game, right? So imagine playing, so you're familiar with, let's say, rock, paper, and scissors, right? So there's two players, right? Simultaneously, like one goes rock and the other goes scissors, and rock beats scissors, okay, because rock can break the scissors. But scissors can cut the paper, etc. Right? You probably know this game. Otherwise, just check it out. So, if you play any deterministic strategy for rock, paper, scissors, right? Then there is an opponent who can beat you all the time, right? When you play rock, they will play paper. When you play paper, they will play scissors. When you play scissors, they'll play rock. The only way you can beat that is to randomize. Okay, you need to have a strategy that's picking rock, paper, and scissors with non-zero probabilities. Okay, so optimal policies in such games, right, and many other formulations of games when players are playing simultaneously, is they have to be randomized. Okay, so in the game literature, policies are called strategies, and stochastic policies are called mixed strategies. Okay, we will probably have 1 or 2 lectures on multi-agent learning towards the end of the course. But again, right, I hope it already helps you as an example that there are variations of the general theme that we have studied. That you have a different reward structure, or you have non-Markovianness because of partial observability or because of another player, right? In which case you can you can actually help yourself by being stochastic or using history. Okay. Look out on the course page. I will write a more technical definition of history-dependent stochastic policies and say why they don't help when we are maximizing infinite discounted reward. Okay, all right, good. So, what have we done? We have seen a proof of the policy improvement theorem and some arguments to the effect that what we've done is enough. Okay, so let's not worry about history and stochasticity. We have actually shown that there must exist an optimal policy. Okay. Now, what's coming up in part 3, okay, is something that you should probably consider as not very essential as a part of the lecture. Okay, so you will probably not find this material in textbooks. It's not covered as a part of courses, but I am going to cover it anyway, right? Because I think this is a grad elective, and presumably there will be some fraction of students who are interested in sort of the research, right, around MDP planning. Turns out I have also myself been working on these problems. So a lot of what I want to present to you is some of the results from here, right, from IIT Bombay, having to do specifically with policy iteration. Okay, and I'm also going to list some open problems as a part of this. So again, I want to emphasize that it is optional, but if you're interested, do follow this. You've basically got the background now, right, based on what we've covered, to understand and appreciate the problems that I'm going to present in this section. All right, so let's begin actually with 2 other families of algorithms, which is value iteration and linear programming. So this slide is going to get a little bit dense in terms of references. Okay, I'm going to refer to a fair number of papers, so I'm not going to put all of them on the class page, but this one paper of ours, right, if you look at this will contain all the references, at least most of them, I think, right, that you will find listed on this page. Okay, all right, so first let's look at value iteration. The idea of value iteration is that you will start at some arbitrary mapping from states to numbers, and then keep applying B star and end up in V star, right, which is also V pi star. Now, how much time does it take, right, to reach an optimal policy? or rather the optimal value function. Right? We know that in principle it can take an infinite amount of time, right? However, in practice, right, you are almost always, in fact, you are always in practice given an MDP that is like represented using a finite number of bits, right? In theory, you can have an infinite number of bits, but in practice, it is some finite number, right? You have 64 bits on your machine, right? And precision is determined by that. So it's possible to show that the number of iterations taken by value iteration is polynomial in the number of states in the MDP, the number of actions in the MDP, 1 over 1 minus gamma, right? Remember that gamma is our discount factor. So 1 over 1 minus gamma, it's like a proxy for the horizon, right? It's sort of saying how far ahead do you need to see, right? In order to assess how much something is going to affect your value. But the other way of saying it is things beyond 1 over 1 minus gamma, right, of your future will not really affect your value. Okay, so that is another. Here, the dependence is a polynomial in the number of bits. Okay, so you will basically stop when up to bit precision you're not able to separate out VT plus 1 and VT. Remember, so that will happen after a number of steps. That's polynomial in the number of bits. Okay, so this is a bound for value iteration. You can look up the paper, Kelbling and more, I think. What about the linear programming approach? So linear programming has received a lot more attention in the literature over the years. So linear programming admits algorithms that are polynomial in the number of states, actions, and the number of bits. Okay, so this was a sort of celebrated when people came up with like interior point method, ellipsoid method, etc., and showed that if you're given a linear program that is taking, I don't know, b bits, right, of space to just represent, right? So in time polynomial in that, right, which is also like polynomial in number of variables and constraints, you can compute the answer. Mathematical way of saying, by the way, that linear programming is in P. Okay, and for that reason, because MDPs can be written down as linear programs with n variables and nk constraints, or vice versa, right? It follows that MDPs are also in P. Okay, in the complexity class P.